In this video, we're going to go through what's really our last topic when it comes to determining bending stress for this course, and that is looking at unsymmetric sections or sections which are subjected to biaxial bending. And so, previously we've looked at sections which have at least one axis of symmetry. So whether they're rectangular, circular, triangular, an I section, even a T section has at least one axis of symmetry. But we've never really seen anything like this, where we've got, an angle section. And, what I've sort of drawn out here schematically is I've sort of told you that, if you're going to bend an angle section about, parallel to one of its flanges, not only will it bend down, but it's also going to want to rotate. So I kind of want to demonstrate that. So I have this foam angle section here, and I'm going to bend it in this direction here, sort of about this flange. And so just watch the middle, and you see how it's just rotated. So I'm bending again, and it just wants to rotate. And all I'm doing, I'm not trying to kick it over. In fact, I'm trying to restrain it from rolling over. But you can see that it's just trying to rotate over as we do that. So, what's happening? Now, if I rotate it and I'm going to bend it, say, about its spine, look at what happens. It just bends actually quite nicely and sort of how we would expect. So there's something going on here. And the real question is, well, why does this happen? And obviously that's what we're going to look at in today's lecture. And it really just doesn't want to bend nicely about sort of an X or Y axis. And I guess one thing to keep in mind is that, we've always used these X and Y axes as really, parallel to some axis of symmetry or some geometry within the section, but they're really an arbitrary definition of what our axes should be. And so that's, I think, maybe the first thing to keep in mind, is that there's really nothing special about X and Y. We're just used to working with them, so that's what we've used so far, and so far it seemed to work pretty well. But obviously, once we get to this sort of unsymmetric section, it's not working so well. The next thing is that, well, why do we have this phenomenon with an angle section, but we don't have it with a rectangular section? So what's different about this that we aren't seeing? And the difference is really what's called, it has to do with the principal axes of bending. So every section wants to rotate about its principal axes. And these are going to be defined by the point, or sort of the axis by which either side perpendicular to the axis that you're bending about, the first moment area is going to be balanced. So let's sort of show a sort of schematic definition of that, and we'll use this angle section as our definition. All right, so if I've got this angle section here, and I'm bending it about the XX axis. Now, my areas might be balanced about the centroid here, but the first moment area isn't balanced. If we think about sort of the areas as equivalent to, some force, and then, the moment arm for the first moment area equivalent to some length on a seesaw. Well, if we're going to sort of use our pivot point at our centroid, well, obviously we're sort of unbalanced here, where we've got, some, longer distance over here than we do over here. And so that's really going to cause our section to want to rotate around. While if we're bending about sort of the spine of the angle, well, now all of a sudden, our areas and the centroids of the location of those areas to our centroid is the same. So, that 80 squared bit that we have for our parallel axis theorem is all sort of working out nice and balanced there. And really, this is what it means to be in the principal axes, is that you're going to be bending around one of these axes where you have the first moment area balance between the two. And so, if we have, these principal axes would be sort of U and V in this case instead of X and Y. Well, we need to work out, how do we determine what these are? If they're going to be rotated some angle theta from our sort of familiar Cartesian X and Y coordinates, and we know what the moment of inertia for the X about the x-axis is, and about the y-axis, we know how to find that. Well, if we know these two things, well, how do we find this angle theta? And then how do we find our corresponding moments of inertia about the u-axis and the v-axis so that we could say work out what the bending stress is, here or here. And that's really what we're going to be covering in the lecture today. So, and really the first step of sort of determining what the mathematics are of this is to introduce this concept called the product of inertia. So the product of inertia, it's very similar to the moment of inertia, except, how we would, second moment area. So say we want to do the second moment area about the x-axis, would be dA times y squared, and we'd integrate that over the entire section. But for the product of inertia, we actually define it with respect to two axes at the same time. And so instead of this being sort of a y squared or an x squared, it's going to be, the integral of x times y over the whole area. And so similar to like our moment of inertia, we can turn this just simply into a sum. Now, one of the sort of things that you would not have been familiar with before if you've only looked at the second moment area or first moment area is that the product of inertia can be positive, can be negative, or can be zero. And in fact, when it's zero, that means that you are on an axis of symmetry, and that you are actually, in fact, on one of the principal axes. So this is, maybe the first key that we have around determining, when do we have this, when are we on this principal axis? Well, it's when this sort of magical cross-section property of the product of inertia, when it equals zero, well, then we know we've hit a principal axis, and we know that, for our angle case, it's going to bend nice and evenly like we would expect. And so similar to, we have a parallel axis theorem for, our second moment of inertia. We also have a parallel axis theorem for the product of inertia. And it's simply the same thing because where you're just going to increase what your lever arm is, but it's going to be the product of inertia about some axes plus the product of inertia of whatever point you have about its own centroid. But if you're on the principal axes of these, this equals zero. So just want to sort of show you what that looks like with a quick example. And so we've got a T-section here. Now we know a T-section is going to behave nice and symmetrically. It's going to bend. If we're bending about the XX axis, it's just going to bend, down like we would expect. It's not going to do any weird twisting. And so we kind of want to show that by determining what our product of inertia is. And we know that if our product of inertia equals zero, we're on a principal axis. And if we're on a principal axis, well, that means that we're going to be bending straight down instead of trying to rotate to some other axes. So let's work out what the product of inertia is about the y and x axis defined at the centroid. So as I said, all of the product of inertia is, with respect to two axes. All right, so to do that, let's break this into a few little pieces. We'll break it into kind of piece 1 up here, piece 2, piece 3, and piece 4. It'll have some centroid of the top half of the flange around here. And it will have some distance between the centroid of the entire section, a centroid of its own. So we'll call this y1. We'll call that x1, x2, y2, and we'll call this one y3, x3, x4, and of course y4. All right, so these are where we've broken up the cross section into kind of 4 distinct little pieces. I'll just hatch them just so they're a little bit clearer. And we want to find the product of inertia of all of these relative to the centroid in the xy axis. So if Ixy is simply going to be the integral of xy dA, and that's equal to the sum of x of I times y sub I times the area of I. Well, that's just going to give us, we can just go through like we would for the parallel axis theorem and just look at, the area of each of these little pieces and its distance x and distance y from the centroid. And the only thing that we have to keep in mind is that our distances could be positive or they could be negative. So we'll start with, the piece number 1 is going to be equals a negative 20 minus 10. So that's going to be equal to, x1. So, 10 distance here, 20 there. Multiplied by, if our y bar is at 51.1 down, we would be 51.1 minus 15 y1, and then multiplied by 30 times 20. And this is the area one. Then we would add up our, plus 20 minus 10. So for 2, our x distance is positive. And then we'll have the same y distance, 51.1 minus 15. And the same area, 30 times 20. So this is x2, y2, area 2. And then we'll add in our distance 2 for y3, which is simply going to be minus 3.75. So it's coming over 3.75, so half of 7.5. Distance here to here. But we're going in the negative x direction. Times, our distance here will be 80. So 30 plus half of 150 minus 51.1. 1.1 minus 80 times 7.5 times 100. So this is x3, y3, a3, and then now we're going to go in the positive x direction. So instead of a minus, we're just going to be 3.75 times 51.1 minus 80 times 7.5 times 100. And this is, of course, x4, y4, area 4. Now, if we see all this, well, because it's symmetric, we've got, minus all of this plus the same thing, so that cancels out to 0. Minus all of this plus all of this, so that cancels out to 0. So we have I, xy equals 0, which means x and y are principal axes. Cool. So that's kind of good to know. And again, this shouldn't be, overly exciting and new. This is really just sort of running through this new concept of the product of inertia with a section which we've seen before. And, if we've bent a T section, we know that's just going to bend down. But now we have the math to prove that that's going to happen. And the reason that it's a principal axis is, you're symmetric about, the axis, of, perpendicular to what you're bending. So if you have at least one axis of symmetry, well, that's going to be your your principal axis. Again, thinking around sort of the angle section here, if these two angle sides are the same, well, our axis of symmetry is right here. So yeah, that's our principal axis. So that's all starting to, be consistent and should start making a little bit of sense. So now we've got the product of inertia And well, that's helpful, and we know that'll be used somehow, and we know that if we're trying to find principal axes, it's when this product of inertia equals 0. But still we want to work out, well, how do we find out what this angle by which the principal axes are rotated is? And so in order to do that, let's look at the rotation of our principal axes. And so if we again set up our generic engineering blob, and say we've got some principal axes u and v, which are rotated at an angle from theta. And we can set up sort of some of our classic section properties or properties of plane sections, where moment of inertia about the x-axis is obviously second moment area about the x, moment of inertia y, second moment area about the y, and then we've got the product of inertia about the x and y. And we really want to see, how do these change as we rotate through to our principal axes? Because, ix and iy are what we use to find bending stress. Well, we know that those are going to be set up relative to these axes. But if, the element really wants to bend around u or v, because it naturally wants to bend around the principal axes, well, we have to change our moments of inertia somehow. And, effectively what we're going to do is rotate this around until ixy equals 0, because by definition, that is when we're at a principal axis. So just like we said here, we're at a principal axis when ixy equals 0. So if we do that, we can rotate around, and then we can find, how to ix, how does that become iu, and iy, how does that become iv? So just setting up some mathematics here and sort of relationship between our x-axis and our u-axis. So u-axis is just going to be, x times the cosine of the angle theta plus y times the sine of the angle theta. And the v-axis is going to be y times the cosine of theta minus x times the sine of theta. And so if we do all of that, and we skip through all of the calculus, to go from our second moment areas and skip through the trig identities, what we end up with is the relationship between our sort of Cartesian x and y, moments of inertia, to our principal axis, moments of inertia, are these big giant equations here. So you've got moment of inertia about the u-axis is ix plus iy over 2 plus ix minus iy over 2 times the cosine of 2 theta minus the product of inertia times sine of 2 theta. And then similarly here, you've got the principal axes about the v-axis coming from, if we know ix and iy. And for those who've seen it before, you can also get to these same things using Moore's circle. So we'll just have that. Can also using Moore's circle. But we won't go through that today. If you're familiar with Moore's circle, you'll see that these, or stress transformations, you'll see these are very similar in form. And that's really how we get there. So, all right, well, we now have a moment of inertia and about, both principal axes. They're kind of big, ugly equations, but they're, we know all these bits and pieces. We know how to calculate ix, we know how to calculate iy, we know how to calculate ixy. They're pretty straightforward. And then it's just sort of plugging in and sort of keeping track of all of the algebra and the arithmetic. But still, what we haven't worked out is, what is the angle by which, we get from our Cartesian coordinates to our principal axes. Well, if we know that if ixy equals 0, it's the same as, it'd be when the principal axes, when its product of inertia equals 0, which, here's the product of inertia of our principal axes. When this equals 0, well, we know that we're at our principal axis. And so if we set all of this equal to 0, and we skip through all of the algebra, what we get is that the angle, theta p, of our principal axes, so the tangent of 2 times that angle is equal to negative 2 times the product of inertia from our Cartesian coordinates over ix minus iy. And if you solve this, you'd find that you actually get two solutions, and they're 90 degrees apart, which should make sense because our principal axes are 90 degrees apart. So, that's, again, a bit of hand waving there, a bit of just, this, we'll sort of skip through a lot of the derivation, which is effectively just a lot of mathematics, which is not really what we're trying to test you here. But I think the key thing to keep in mind is that, these things called principal axes exist, and they're really what you want to bend around, and they're going to be when your product of inertia equals 0. And so if you can calculate your moment of inertia about any given axis, Ix or Iy, well, you can turn that into your principal axes using these equations. So that's how we get to our properties of plane sections of it, and that's all well and good. But really, what we care about in structural engineering is my section okay? Can it carry the load? And one of the critical ways that we look at that is by what its stress is. So now the question is, how do we go from all of this to a bending stress for, a given biaxial or unsymmetric problem? So for biaxial bending stress, again, now we know how to find our principal axes U and V, and we know how to determine the moments of inertia about these axes. We know how to find IU and IV, and like I say, they're kind of ugly equations, but we can work out, how to get to all of those. They're just a set of equations. We can always look them up. It's not that hard. But now the case is like, well, if I've got some bending, how do I apply these? How do I do something useful with them? And really, the key is going to go back to what we've learned when we did combined actions, and that is use the principle of superposition. And again, the big caveat is this works as long as the material is elastic. So I'm going to present two cases for you, which are going to utilize these principal axes. The first case is when, you're actually bending about one of your two principal axes, or you're bending about your principal axes in two different directions. And so what we've got here is a rectangular cross-section, and it's got some bending about the x-axis and some bending about the y-axis. Now, we know that the x and y, as they're defined here at the centroid, are the principal axes. This is going to bend nice and easy. We can also prove that by calculating Ixy. We know that it equals 0. So what we're going to do is basically just do some quick substitution and say that, well, because we're on our principal axes, we know that our x-axis is going to be equal to our principal u-axis, and our y-axis is going to be equal to our principal v-axis. And so similarly, mx is going to be equal to mu, and my is going to be equal to mv. And again, just as a quick refresher, when we've got these double pointed arrows, we point our thumb in the direction, and then our fingers curl in the direction that the moment's being applied. So here, being applied like that in the mx, and being applied like this in the my direction. All right, so now that we have that, I say we can use superposition. So how do we apply the bending of this? Well, schematically, what we do is our total bending stress is simply going to be equal to the bending stress about the u-axis plus the bending stress about the v-axis. And then we're just going to add these two together. And so if we're already getting bent about the principal axis, it's actually pretty straightforward. All we have to do is, effectively this is similar to our form of my over I. So our applied moment times our distance away from the neutral axis over the moment of inertia about that principal axis in both directions. And so practically, how do we apply this? Well, so you see I've got some labels of A, B, C, and D on this cross-section here. And so, what I like to do is just simply set up a table where, at point A, I know the distance away, and I'll just, again, with here, it's sort of important to keep track of your coordinate system and which way is positive and which way is negative. It ultimately doesn't matter as long as you're consistent, but, typically we would have, as you're pointing towards the tension side, that would be like your positive, V or your positive U direction. And so, and again, if you ever get confused, one way to think about it is, well, if you're bending this way and you're bending this way, Well, you know that C has to go into tension because, both moments are pulling away from it. And you know you're going to have a principal axis, going somewhere like this. So it's also useful to sort of think about what's happening with the section as you go through these in order to help make sure you're consistent with your sign convention. So as I said, what we do is like go to point A, and we'd work out that, from our centroid, we'd be, say, negative b over 2 away. That's our u value. And we're a positive d over 2 away. So all we have to do is plug in negative b over 2 into u and positive d over 2 into v. And then we can work out what our stress is at A. And we can do the same thing at point B, at point C, and at point D. And then we can simply plot that up. And so our stress distribution from this biaxial bending would look schematically something like this, where, the top is really going to go into compression, and then at point B, and point C is really going to go into tension, because we know the bending moments are going in both of those directions. And it's sort of going to, I guess we've got something like that going on. So that's pretty straightforward in terms of just finding the magnitude of stresses. And for the most part, that's really what we care about, is the magnitude of stresses when we're doing a design. However, the only thing that we don't know is really, what is this, angle of the neutral axis? At what angle theta? So, we and this is because we're already working on our principal axis. Well, let's say, instead of calling it alpha, instead of calling it theta, let's call it alpha. I like alpha here. So what angle alpha? Well, how do we get there? So, again, how do we find the angle of our principal axis? Well, we know that our neutral axis, by definition, is when our stress equals 0. It's when we've got no strain. And if we're an elastic material, stress is going to equal strain due to Hooke's law. So, how do we work out when our stress equals 0? Well, let's just set our bending stress equal to 0, right? So that's pretty straightforward. And then really it's just an exercise in algebra. So if we want to know the angle of this, well, it's really going to be some rise v over some, horizontal run u. And we could set this as a little triangle. And we know that the angle alpha that the neutral axis is sitting relative to our principal axis u is just simply going to be the tangent of alpha is going to be v over u. So we've got a v, we've got a u, we're setting this equal to 0. Let's do some rearranging. So v over u equals mv over iv, mu over iu. And so if the tangent of alpha is v over u, we know that the value of alpha is going to be arctangent of v over u. So we can substitute in, our equation of our moments over our moments of inertia. And we end up with the fact that alpha is simply going to be the arctangent of mv over mu and iu over iv. And sometimes, maybe I'm going to sort of circle two different ways to find this. So if you're given a problem and you've given it sort of like this, where you've got two moments about two axes and they're defined, well, it's actually kind of easier to find alpha simply by just sort of plugging it into this big equation, because you already know IV, you know IU, you know MV, you know MU. That's pretty straightforward. Work out an arctangent. Your calculator's doing most of the work there. But sometimes you're given a problem where it's not necessarily that you've got, two, orthogonal moments which are sort of given to you in this fashion. Sometimes you're given a problem where, you've got a beam which is sitting at some angle and it's getting pressed on. And so, you've got a resultant moment coming about two different directions. And so, well, if you know the angle here, theta, well, sometimes it's easier to just work out from an angle based upon your ratio of mv over mu, tan theta, and this is really just sort of our way to get into a resultant moment, right? This is, that theta is just the resultant moment going in this direction here, some theta up. Well, if you know that, again, sometimes these just take from a theta, IU over IV. And again, these are equivalent. This is all kind of doing the same, but sometimes you're given information in a problem where it's a bit easier to apply it in this manner. But if you ever get confused, this will never take you wrong. All right, so that's case one where we've got biaxial bending about some principal axes. And really this is just an extension of what we've done so far with sort of symmetric cross sections where we're already bending about a principal axis. This is now, well, how do we deal with bending in the orthogonal direction? Now case two is sort of what we started off today with. So say that we've got a non-symmetric section, or we're bending about a section not about the principal axis. So we've got our angle cross section here. Well, really, all we're doing with that is effectively the same thing as our principal axes, but we don't know IU, and we don't know IV, and we don't know MV, and we don't know MU. So we have to use some way to transform them based upon our rotation of our principal axes in order to get there. And so effectively we need to use these big ugly equations. But if we do that, and we do a little bit of simplification and sort of skip all of that algebra, and I just sort of give them to you, well, you're stuck with really two forms where you've got my times ix minus mx times the product of inertia times the distance x over ix times iy minus the product of inertia squared plus the applied moment in the x direction times iy minus the applied moment in the y direction times the product of inertia times the distance y away from the centroid, neutral axis there, over, again, the same thing, ix times iy minus the product of inertia squared. And so, again, it's kind of an ugly equation to deal with, but we know all the bits and pieces, and we know how to find all of them. So this is really useful when, you have, maybe you're bending this about, you have this set up as a beam. It's got a support along this bottom flange. It's going to have some bending mx. It's not going to have any bending my, so the my's cancel out. And then you're just working out your product of inertia and your moment of inertia about the y-axis. And so in that case, that's actually not that difficult to deal with. You just have to do a little bit of bookkeeping and keeping track of the equation. And so, again, that's how we find bending stress. And as I said, it's completely analogous to when we've got our principal axes, but it's simply just using the transformation equations to go from our Cartesian coordinate system to our principal axes. And so just like with case one, when we have to find our neutral axis, well, we can find it by setting all of this equal to 0, because it's when our bending stress will be equal to 0, is when we're at the neutral axis. And if we do that, well, these two kick over, and we can factor these out, and they would cancel out to 0. And so we just get my times ix minus mx times the product of inertia times x plus mx times iy minus my times the product of inertia times y. Well, really, we have a constant times x plus a constant times y. We can separate those out, and again, we can use the same fact of you've got some to find this angle alpha. It's really just the tangent of the rise over run. So arctangent of y over x is simply going to be arctangent of this big old thing. And again, there's nothing other than the product of inertia, which is you haven't learned how to find before. And again, this is effectively the same procedure as case one, but it's really the one to use when, sometimes it's easier if you're just starting with a section where you're not going to be bending about the principal axes, because ixy will not equal 0. It's often just easier to apply this formula straight off instead of going, using these big equations to get IU and IV and then plug those in to this one. Well, if you're already starting here, just use these equations. And you're doing the exact same thing. It's just handling the transformations for you with, minus a few steps of additional algebra. So that's ultimately the procedure for doing bending either about a non-principal axis or biaxial bending, because they're effectively the same. You're going to bend, if you're just bending MX, as we saw here, well, you're going to do, you're going to bend about both axes because we're not bending about a principal axis. So that's really just our steps there. Again, a lot of mathematics, a lot of equations, but really the application of them all comes down to this, superposition, and then, understanding, the angle of our neutral axis is simply going to be when our bending stress equals 0, and then we can work that out some pretty simple arithmetic there. So hopefully you found that somewhat straightforward. Once it's broken down into those pieces, we'll do a few examples and sort of show you how to apply this. So with that, thanks for watching.